Okay. Good morning. So today, last time we did facciamo un riflesso, forse. Scrivo qui. Sì. Provare ad appostare un po'. Sì. C'è ancora, sì. Temo che forse bisogna chiuderla questa, perché sennò non si vede. Se si può aprire quella di dietro, magari. Non so se cambia qualcosa. È una roba uguale. Queste non si aprono, sono persone autorizzate, qualcuno deve controllare. Ah, sono rotte. Perché con i riflessi mi pare che poi non vedono di casa. Tanto adesso si è anche defocalizzata. Vediamo se si riattiva. Aspettiamo che si focalizzi, Tanto scrivo. Okay. Allora, so last time we did the Ising model in one dimension, and so in basically a chain of spin, if you want, and we could solve the problem analytically and without any approximation because we could get the analytical formula for the canonical partition function from which then we derive for the thermodynamics. And in particular, what we saw is that there is no phase transition in that case, in the sense that, in principle, the situation in which all the spins are aligned is realized only when t is equal to 0, basically. So there is no phase transition. Phase transition would correspond to a case in which the temperature at which this phenomenon occur is a finite value. Okay, it's a finite value temperature. And this is going to happen instead in 2 dimensions, and we will do it in this 2-dimensionalizing model. But the calculation analytically can be done, but it will take many hours. If you are curious to see, you can look at the solution of Onzager in the book of, for instance, Gerson Wang. We will use instead the mean-field approximation, which is a reasonable way to understand the qualitative features of these phase transitions in the Ising model. Okay. So the starting point is to write down the Hamiltonian. Okay, first of all, the situation we are looking at is something like this. So we have a lattice of particles that have these 2 degrees of freedom. Well, these degrees of freedom associated with the spin, which could be up and down, or plus and minus. And now, what is the difference with respect to the previous case? In the previous case, we had just a linear chain, which was then connected via periodic boundary conditions. Whereas here, we have, of course, more interactions in the sense that, for instance, if you take this spin, the closest spins are those ones. So there are 4 of them. Then there are these other ones, so other 4 of them, etc. So there is a sort of hierarchy of interaction between this spin and all the other particles that reasonably should scale, well, should decrease as a function of the distance. So we expect the interaction to be stronger for the closest, and then to get weaker for particles that are more far away. Okay, so the starting point is to write down the Hamiltonian or the energy by working in the diagonal basis, and we write this as follows. I will explain in a moment what is the meaning of this minus h. Now A is as before a magnetic field external. As the previous case, and the structure is actually very similar. So we have the coupling between the spin and the external magnetic field as usual, and then we have a coupling between the spins among themselves, regulated by an interaction strength, which is the Hestes epsilon. And here we have a sum over two indexes, which is I and J, which is the sum running over the closest spin. Okay. Over the closest ones. For instance, for that we will use later. So each spin interacts with the closest four spins, for instance, okay, or could be 6, or could be at this level is just a way to say that these spins are interacting with the neighbors. Okay, we will specify later how many of them we are going to use. Okay. Let me see if I have to introduce here. Okay, it's not yet. Okay. And at some point, we wrote down also in the Ising model in one dimension the total magnetization, which is basically the average ensemble average from 1 to k of Sk is the magnetization. And let's call m, small m, the ratio between m and the number of particles, which can be regarded as sort of average magnetization per particle. Okay. Now, the difficult part of this Hamiltonian, of course, is this one, because the other one is very simple. It's the action of an external field, and we know that in the canonical ensemble, these are very easy form for the Hamiltonian. Of course, the interaction among particles is the difficult part. So we need approximation. Okay, we need approximation, and suppose that we write the spin of particle I as an average spin. Let's call it Si, which actually will correspond exactly to m, because this is the average spin per particle, or average magnetization per particle. And plus a fluctuation, delta Si, will correspond to fluctuation. So how much the spin of this particle is fluctuates around the average value, the average over the ensemble. Okay, so to compute this quantity, basically it's computing an average ensemble like this one. Okay. And now, if we write this now this product Sij, by using this formula, so we get the following. So S I plus delta S I times Sj plus delta Sj, which is equal to Si Sj averages, and I have the double product. So Si delta Sj plus delta Si Sj average plus delta Si delta J. Okay. Now the mean field approximation consists in neglecting the subleading terms in the fluctuation. So basically, mean field neglect this term. Okay, so up to this level we have no approximation. Once we write, so here we just write our ignorance on the fluctuation is delta Si, and the mean field approximation is basically the assumption that those fluctuations are small, and therefore the product of two fluctuations is even smaller. And so we can neglect basically this term. Okay. In this fashion, we can write again the product Si and Sj as follows. So Si Sj, which appears in the Hamiltonian, now is this guy here. And let me already make some notes at this level. So basically, Si and Sj corresponds to M. First of all, Si and Sj are equal for translational invariance. Because I do not expect the average spin to be dependent on the position. So therefore, Si is equal to Sj equal to M, is the average magnetization per particles. And so here we can write M squared. First, let me do the calculation. Okay, we'll write this later. So I have this Si plus delta Si. Okay, so this was Si and Sj was this one. Then I have plus delta Si, sorry, average of Si times delta Sj. What is delta Sj? Is Sj minus the average. Sj. Okay. So for Sj minus J. And similarly for the others, so I have the average Sj times this term here, average delta Si, and delta Si is Si minus the average. I will use this in a moment. Okay, so this is just now Si Sj plus Si times Sj, this minus Si Sj, this plus Sj Si minus Sj average. Okay. Now this term drops. This is equal to Si Sj plus Sj Si minus Sj. Okay. Now we can use this translational invariance, and first of all write that Si, the average, and Sj average is equal to M. Therefore, here we will have M times Sj plus M times Si times M squared. Okay. Which is equal also to M Si plus Sj minus M squared. Okay. Now this is useful. This is also equal to M Si plus Sj minus M. Okay. And this is the starting point, Si Sj is equal to this immediate approximation. So now I can write back again the Hamiltonian of the energy in midfield approximation. And this is equal to, okay, the term which is the coupling with the external magnetic field that I haven't touched, which is the following. And then I have a minus epsilon. I can collect out of the sum, I can put this M because it's a number. And then I have the sum over this fancy symbol, indexes, I and j. But now I can substitute this function here, which is Si plus Sj minus M. So this is the Hamiltonian in field approximation. Okay, where you see that there is no product of Si and Sj anymore, which was the difficult part, because this is basically the interaction between spins. Whereas here, as you will see in a moment, the interaction between particles is sort of averaged, and actually is, can be somehow hidden in an effective external magnetic field, as we will see in a moment. Okay? And this is the meaning of the mean field approximation, in the sense that you basically you are assuming that the interaction between the particles creates a sort of mean field in which all the particles feels. And this mean field is a sort of an external field, therefore it's easy to be included in the calculation. Okay. Okay, but first of all, we have to modify a little bit this expression. So take sum over I and j over Si plus Sj. So first of all, since these indexes are saturated, I and j are saturated, this is actually twice twice Si, for instance. So this is twice the sum over I and j of Si. Okay? Because this expression is symmetric with respect to the exchange of I and j, and therefore it is just twice the same expression, just Si or Sj, and I have still the symbol I and j. Okay? This is the first thing that we do, and then the second I will do it in a moment. when I introduce this, the Hamiltonian now reads, well, let's write it down here. So the Schmidt field Hamiltonian is, as before, the same term. We have minus epsilon n from 5j. And here you have 2 s n. Okay. Now we can actually make it even easier in the sense that so here what we are doing is to sum over the closest spin, and you see that if I fix I and I run over j, basically I'm running over all the neighbors with which the particle is interacting. Suppose that we have a case Q, sorry, it's the number of the closest spins with which we have interaction. Now, since this index, so this function here inside the sum does not depend on j, basically this sum is telling me that I have to do twice Si times the number of closest spins with which the particle is interacting. So this term actually will look much more simpler. So I have epsilon m, and then I have, as you see here, there's no dependence in j, and therefore, actually, this term will correspond to a sum from I, if you want, from 1 to n over 2 Si minus m times q, which is the number of particles with which Si is interacting. Okay, so let me repeat this. Here I do not have a dependence on the index j, and I'm summing this term over all j. So therefore, since I do not have a dependence on j, how many particles I have interaction with? Number q, and therefore I just have a q here. So this double sum actually becomes a single sum, and of course this is it's a very important simplification. But now I have still to correct this by a factor of 1/2, because here I have Si, and this was a choice to write the previous sum, which was Si plus Sj, and I decided just to put Si, but I could have put also Sj. And therefore, I have, in order to avoid double counting, I have to put a factor of 2 to avoid double counting. If you want, before, so when I did this, if you want, I can put the double counting correction also here, because here I could have written, instead of Si twice Si, I could have written Sj. So to avoid double counting, I have to take a factor 1/2. Okay. Okay. Explanation is there. Since here I'm running over I and j, and this expression is symmetric, this is twice, but then I do not have to include the term, the interaction Si times Sj is equal to Sj times Si. So therefore I have to put a factor 1/2 to avoid double counting. Okay, so I think that now it's basically done. Now the Hamiltonian looks field Hamiltonian has this form. Okay, and then I have, let me see if it's convenient to write this. Yeah. So then I have plus epsilon m squared q divided by 2, which is this times this. So this epsilon m 2 divided by 2 squared, and we should have a factor of n comes from the product of this and this, but this is the sum, does not depend on the index, and therefore I have a factor of n. So it's nm times this guy here, and I should get this epsilon squared qn divided by 2. Okay. And then, of course, what is left is this here, which is minus epsilon m q sum 1 to n over sk. Okay. Which can be seen as epsilon m squared q n divided by 2 minus sort of effective Hamiltonian times the sum from 1 n of sk, where this effective kinetic field, what I said Hamiltonian, magnetic field, sorry, is h plus epsilon and q. Okay. With an effective. Okay. So therefore, you see that in the mean field approximation, the Hamiltonian now looks very simple because I have this term here, okay, and then the dependence on the spin or the degrees of freedom, which is in this case are the spins of the particle, is very similar, well, is actually equal to a case in which all the particles are independent, but they interact with an external field. And those are the situations for which the canonical partition function is very easy to compute. Okay. For instance, we've done many examples in which we have also a gas or particles free to move in space within an external field. It could be a gravitational field, an electric field, whatever. But since particles are independent, the calculation of the canonical partition function is very simple. And also in this case, the situation is as follows. Okay. So the only difference with respect to a real external field is that we have this additional term that actually is responsible for the interesting features that we are going to find concerning the phase transitions. Yeah, so the Hamiltonian, now we can compute indeed the canonical partition function is the Hamiltonian or the energy, and we can compute it in a simple way. So the canonical partition function is the sum over S1 over Sn. Now, if we had a coupling here between particles, computing this sum would be very difficult. But instead here we have just this now. So we have e to the minus beta times this term here, which is epsilon m squared qn divided by 2. And then we have this other term, which is e to beta. Let me see if I yes, e to beta H effective, and then we have the sum from K to N of Sk. Sum K of Sk. Now let me see which is the form of this exponential. Is d beta H effective times S1 times E beta H effective times S2 plus all the others. And so you see that this term does not depend on S1 and S2 and Sn. I have the dependence in the exponentials, but they are decoupled. So then I can do the sum in a simple way, in the sense that I have this term that can be taken outside, epsilon m squared cubed n divided by 2. Then I have the sum over S1 of e to beta H effective S1 times the sum over S2 of e to beta H effective S2, blah, 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 up to sum Sn of e to beta H effective Sn. Okay? So the mean field operates in such a way to decouple basically the spins of the particles and to include the interaction in a sort of an effective way here and here. Okay, so now the canonical partition function is actually very simple because here I have the exponential of beta epsilon m squared q n divided by 2. When I do the sum here, S1 runs, let me write it explicitly, from -1 to 1, which are the two possible values for S1. And therefore, I will have exponential of beta H effective, the plus the exponential of minus beta H effective, which is a 2 cosinus hyperbolic of beta H effective. And how many times I have to do it? N times. So this is the power of n. Okay. And so this is finally the canonical partition function of Z. Which, as usual, remember that when we have independent particles, the canonical partition function is just associated with the system of n particles, is the canonical partition function of written for one particle to the power of n. Okay, because it works like independent particles instead, and indeed we have this power of n here and here, which correspond, if you want, to a z or 1c of zc1 to the power of n. Okay, now with this we can do all the thermodynamics once we have the canonical partition function, and we could write it in a very simple way by using the mean field approximation. And now we will see what happens. Let me see what is convenient to do. Okay. We can do the thermodynamics. So first of all, we can compute the Helmholtz free energy, because e to the minus beta A is equal to z to the canonical partition function, and therefore we can write the Helmholtz free energy, which is a minus ABT, and then I have to do the log of the canonical partition function. So minus KBT is outside, and then I have to do the log of this expression here, which is minus beta epsilon m squared q n divided by 2 which is the log of this function here. Then I have to do the log of this, which is n times the log of 2 cosinus, etc. So plus n, and we have log of 2 hyperbolic cos of beta at h effective. Maybe let's put a bracket here. And out of these, let me collect a factor of n in here, and I get the a divided by n is equal to minus kbt times, well, this function, same, square q plus log of 2 cos h of beta times, what was h effective? H effective was the magnetic field H plus epsilon and q we wrote before. And let's close this. Okay. Now it's a matter of calculation, and we see what happens. First of all, the first thing we would like to compute is m. See previous lecture. M can be is the average magnetization of particle, can be computed by using the canonical is an ensemble average, and can be computed also by using directly the Helmholtz free energy by deriving with respect to h. See, we have done this calculation last time. So we can basically do the following: is minus the derivative with respect to the magnetic field of A divided by N. Okay. So then I have to take this function here and derive by N. That means that M is equal to the derivative with respect to H of this function here. Okay, so I have, let me see, a KBT with a minus. Then I have to do the derivative with respect to h of this function here. Since I have a log, I should have here a 2 cos hyperbolic cos of beta times h plus epsilon and q. And then at the numerator we have the derivative of this function here, which is 2 sinus hyperbolic of beta times h plus m epsilon q times beta. And so these two drops, kbt, these beta drops, and then finally m has this very simple formula. So m is equal to the hyperbolic tangent h of beta h plus m epsilon q. Beta h plus m epsilon q. Okay. Now, as you see here, we have an equation for m, which is a nonlinear equation that cannot be solved, can one cannot solve it analytically because I have that m is on the left hand side and the right hand side. Okay, in here and here, and we cannot do much in the sense that one has to try to solve this equation for m, for instance, numerically or graphically, and we are going to do the second. Okay, so let's work first of all. So this is an implicit equation, if you want. Implicit equation. Okay. So let's work first of all in the case of h equal to 0. Let's take h equal to 0, and therefore this m is equal to the hyperbolic tangent of beta m epsilon q. And let's make a plot of this quantity. So these are, let's say, function 1 and this is function 2. Now, the function 1 is just m, and therefore is just a line like this, no? Okay. This is the plot of 1. The function 2 is instead a hyperbolic tangent, and the hyperbolic tangent goes to +1 and -1 at infinity, and it works. It has the following plot. Well, it depends on the temperature, and this is the interesting part now. Because if the temperature is large, here, at fixed m, so here we are making a plot of the function f1 and f2 as a function of m, and we want to find graphically the solution of this equation. Now, for large temperature, you see that at fixed epsilon q, m divided by temperature is small, and therefore this number is small, and therefore for large temperature, the shape of this function is the following. Let's make the plot. And let me use the color, since I have the color. Così che è più bello. So suppose that this is for a temperature T2 large, no? Asymptotically, I should go to 1 and -1, but the tangent at m equals 0 is small, and therefore we have something like that. Now, if you take instead a small value of the temperature, what could happen, and we will see which is the condition for this to happen, is that you reach the asymptotics here before. So you can have a situation like this. Let me try to make the plot in a sensible way, but otherwise you get the wrong result. Or something. So could happen something like that. So this is for T1, where T2 is larger than T1. Okay, so for large temperature, I could have something like this. So basically, the only intersection between F1 and F2 is at m equal to 0. Okay, so large the only intersection is m equal to 0, which is the trivial solution of the equation, what I call asterisk. That is this equation here. Okay. The only solution for this equation is m equal to 0, which is the trivial one. Whereas if the temperature is small, qualitatively, what happens instead is I have the solution at m equals 0, but also I have two other solutions, which are here and here. So actually I get three possible values of m. So for small enough temperature, I have three possible values. Okay. I get the m equals 0, which is the trivial one, and then I have two finite values here, which are actually symmetric with respect to m equal to 0. And actually, which is the condition for which I have these two very different behaviors? Well, the conditions is that the tangent of the two functions is the same at m equals 0. Okay. Because as you see here, if t is large, then this touches the function 1 only at m equals 0. If instead the t is small, the angular coefficient is large, and therefore in this situation I can have the two intersections. So what I need to do is to impose the derivatives of function 1 and function 2. Function 1 and function 2 are the same at m equals 0. So impose. So the critical value of t is found by imposing that the derivative of f1 m with respect to m is equal to the derivative of f2 with respect to m at m equals 0. And this implies that 1, which is this, is equal to, if you take the derivative of the asterisk function, is a hyperbolic tangent. So I have 1 divided by cos h squared of beta m epsilon q times, I'm deriving with respect to m, so here I have a epsilon q. Beta epsilon q is fast to compute for m equal to 0, and the cos h m equals 0 is equal to 1, and therefore this is just beta epsilon q. Finally, I get the critical value of the temperature, the critical temperature, which is now T critical is equal to epsilon q divided by Kz. Okay. And so this is the critical temperature. Which, differently from the case of one dimension, now is has a finite value. Okay. So what I get now, of course, we will study what happens at small temperature. But now, so what happens is that for T above Tc, we do not have a spontaneous magnetization. Because the only solution for m was m equal to 0, which means that there's no preferred direction for the spin of the particles. The average is 0, so it's disorder. Whereas for t less than tc, I have m equals 0, it is a possible solution, but also two other solutions, which are, I don't know, M1 and M2, let's call it M1 and 2, which corresponds to spontaneous magnetization. Which basically means that the spins will have a preferred direction, which could be the one of M1, if it is this solution here, or M2. Okay, so I have a spontaneous breaking of symmetry. Called. Okay, so and this example then is paradigmatic for many other physical phenomena. We will see, not now, but later, that actually, when t is smaller than c, this solution here is a trivial solution, is not energetically convenient, in the sense that one can show that the Helmholtz free energy is actually minimized by this or this. Okay. In a similar way, in the sense working at h equals 0, so without an external magnetic field, actually I will have a value which is this one, or equally probable, this one here, but not this one, m equals 0, because this will be energetically unfavored, well, from the point of view of the Helmholtz free energy. Okay. So let me make some observation before we're going for the break. First of all, so take this formula here, and let's think about what happened in one dimension. In one dimension, Q is equal to 2, and therefore I will get Tc equal to twice epsilon divided by Kb, which is wrong, because actually we have shown that Tc basically is equal to 0 for one-dimensional easy model, Ising model. Okay, this, if you want, is a problem of the mean field approximation. Is due to the mean field approximation. The fact that I do not recover the result for one dimension, but that one was exact. This one instead is computed within the mean field approximation. And as a general trend, one can say that one can show that the mean field approximation works finely, it's good for large dimensions. Okay, at smaller number of dimensions, it breaks down. Okay, so this is a mean field approximation, not good for small number of dimensions. Indeed, we will use it just for understanding qualitatively the features of the phase transition, but the quantitative results are not correct. Indeed, we cannot recover the correct result in one dimension, and also in two dimensions. Actually, I should mention this. In 2D, we get that Tc is equal now to Q is equal to 4, And TC would be epsilon times 4 divided by KB, and for which I also have the number. No, it's not necessary. It's epsilon divided by K times 4, but the correct result, so the correct result, because as I said, one can compute analytically one can solve analytically the two-dimensional Ising model. It's called Alsager solution, and the correct result actually would be TC equal to twice epsilon divided by KB, twice epsilon divided by KB, and here there is a log of 1 plus square root of 2, which is equal to 2.27 epsilon divided by. Okay. So this formula here is a mean field formula, does not allow us to recover the one-dimensional result, because the mean field approximation breaks down in low dimensionality systems, and even in 2 dimensions where it captures qualitatively the features of the phase transition, in any case does not provide the exact value of the critical temperature, which in this case will be 4 epsilon divided by kb, but in the real and any approximation solutions is provided by this number, 2.27. Okay. The fact that we have, and then I will stop here, at t smaller than Tc, we have 2 possible finite values of the magnetization. It's called spontaneous symmetry breaking. For T less than Tc, we have 2 possible values, finite values for M, and this is called spontaneous symmetry breaking. Okay. Which is a phenomenon that you have heard about already, most probably, in particle physics, maybe. No? Modello Higgs boson. Have you heard this term already? Spontaneous symmetry breaking? No? Not yet. Okay, you will do it maybe. Fisica del modello standard la state facendo, no? Un po'. Okay. Non ha parlato ancora di Higgs. Dovete farlo. Okay, well, you will find the same term. Okay. So this spontaneous symmetry breaking at our level here is basically the fact that at t smaller than Tc, we see that we have 2 values of M, which could be a preferred direction up or down, and is of course breaking of the symmetry, because in the Hamiltonian there is no preferred direction. We have just an Hamiltonian which is completely invariant with respect to up or down, whereas here we get that for t smaller than Tc, we have this spontaneous symmetry breaking. Okay, this is a very important phenomenon that could be captured in this scheme, and that is applied. So this concept is applied also in particle physics, as you will see most probably by the end of the course. Okay, so let's stop for a break, and we'll continue in 5 minutes or so. Okay, so let's continue. Now what we are going to do is to
Prof,
start.
sorry, I have a question. I was asking, is this model valid only for ferromagnetism, or in some way we can describe other cases such as antiferromagnetism or other materials?
For the case, well, for instance, what we did last time, which was the one-dimensional, this is a paramagnet. Okay, so this work, so one dimension is a paramagnetic material, and instead is a ferromagnetic. But these are just models. Instead, let's say that are these toy models to study the features of phase transition, are not models for describing magnetism, in the sense that at least the Ising model. Then there are more sophisticated models that are done on the purpose of describing magnetism. Here we talk about magnetization just because it's how to say, it's easy to talk, it's more understandable, but those are models actually for phase transitions. They are too simple to describe what happens in a real magnetic system. Okay, they are much more complicated models. For instance, although the fact that here we have two possible direction, plus or minus, this not does not correspond to a real situation, of course, in which, of course, the direction will be all the possible directions. Okay, there are more complicated models, as the Heisenberg models, for instance.
Okay, thanks.
Okay. Yeah, so as I already said, these are just considered as toy models for phase transitions, okay? And indeed, what we will see that what we have here is actually very similar to completely different situation, which is the van der Waals phase transition, the phase transition that we had in the van der Waals gas. Actually, the behavior, though the systems are completely different, at the critical point is the same, okay? And this is a fascinating subject, which is called universality, that we will barely touch in this course, and you will probably study for the course of Tripiccione, I guess. Okay, so now let's compute the behavior around TC. What happens around TC. So first of all, we want to make a plot of the magnetization as a function of temperature. We know that for T larger than Tc, M is identically equal to 0, okay? Because the only solution that we could find in that case was M equal to 0. Whereas for T smaller than Tc, but and T approaching, if you want, Tc from below, then M is finite for T smaller than Tc, but approaches 0 when T is close to Tc from below. Okay, so in one case, above Tc is identical equal to 0. In the other case, T less than Tc, M approaches 0 as a limit. Okay. Let's also introduce this quantity that is used usually in the literature, which is T, which is the variation from the, well, how far we are from the critical temperature, and this quantity is defined as T minus Tc divided by Tc. So let's introduce this quantity that will be useful in a moment. Okay, so let me start again from the equation of M at H equal to 0, which was the following: is M is equal to the hyperbolic tangent of beta M epsilon Q. Now we are working for H equal to 0, and Tc is actually epsilon Q divided by Kb. Therefore, this is also equal to the hyperbolic tangent of M times Tc divided by T. Okay, this M. Now, suppose that we are working at T approaching Tc from below, for which, as I said before, M approaches 0. Therefore, we can expand this hyperbolic tangent as follows for M approaching 0, which is the case in which T is approaching Tc from below. We can expand the hyperbolic tangent, and this is actually M Tc divided by T, a leading order in M. And the next term is, if you do the expansion, the series of the hyperbolic tangent, is minus 1/3 this guy to the power of 3. So I have M to the power of 3, Tc divided by T to the power of 3. Okay. So what we are computing is the behavior of the magnetization close to the critical temperature from below, from T approaching Tc from below, because from above we know that this is identically equal to 0. Okay. Now this is equal to, I can collect something. So in particular, let me collect M from here. M, and therefore I have well, so here you have Tc divided by T minus 1/3. Here I have M squared, Tc cubed divided by T cubed, and this was equal to M. Therefore, this drops. And I can now find, and this expansion is done for this purpose, in order to find the value of M at small at T approaching Tc from below. Okay, so from this equation, I see that 1 minus Tc divided by T, 1 minus Tc divided by T, plus 1/3 M squared Tc divided by T to the power of 3. Yeah, ho messo quell'1 di là, quello l'ho portato di là. Yeah, this is equal to 0. Okay. 1 minus Tc divided by 1/3. Okay. Of course, I removed M here by assuming that M is different from 0, which is the trivial solution I'm not interested in. Okay, so from this equation now I can derive M. So from this equation I can write that T minus Tc divided by T, and I put this so here I have that 1/3, let me do it slowly, 1/3 M squared Tc divided by T to the power of 3. This guy here is equal to Tc minus T divided by T. Tc minus T divided by T. Okay. Therefore, M is equal to 3 times this quantity, Tc minus T divided by T. Then I have a T divided by Tc to the power of 3. Then I have a square root and a plus minus. Ok? Vediamo se è corretto. Plus minus T minus C. Vabbè. Okay. Now, by introducing the quantity I was mentioning before, T is equal to T minus Tc divided by Tc, I can write this in a slightly different way. So this is actually equal to plus minus. Here I have a 3. Let me see. Here I should have vediamo se non sbaglio, T minus Tc. So here you have to multiply by Tc and divide it by Tc. Then I have a minus. I should have here Tc divided by T. Then I have a minus T. Okay. And then I have T divided by Tc to the power of 3. Sorry, let me see if it is correct. This is the T. Then I have multiplied by Tc and divided by Tc, and there's a minus T. Should be correct. Should be correct. No, che non ho sbagliato le cose qua. Minus 3T. Okay. And then I have this T divided by Tc. And so from here I can see that T times Tc, T times Tc is equal to T minus C. Design. Okay. Then T plus Tc is equal to T, or Tc1 plus T is equal to T. And so here it should be plus minus. Here I have 3 Tc divided by T, I have a minus T. And then I have 1 divided by Tc cubed, and T cubed, which is 1 plus T. And then I have a T cubed. Yeah. So this drops, and this drops. And I think that now I can also write is Tc divided by T. Tc divided by T is 1 plus T. 1 plus T. And therefore here I get something like this. So 3, and I have a minus T, which is there. And here you have Tc divided by T is 1 plus Tc divided by T is, sorry, is minus 1. Okay. T divided by T is 1. Yeah. And then I should get here 1 plus T. If I'm not mistaken. Okay. I will check this calculation. So now what is important to observe, just I can change colleague, that when T is small, now for T approaching Tc from below, of course T is approaching 0, and the minus T is equal to the absolute value of t, because t was defined as t minus tc divided by tc. Okay. Therefore, apart from this term 3, which is not important, here I have 1, and here I have the square root plus minus the square root of the absolute value of t. So m, the scaling of the magnetization as a function of t, so the deviation from the critical temperature, is plus minus the square root of the absolute value of t. Okay? Or if you want, that's fine. Absolute value of t of 1/2. And if I make a plot now of this quantity, I can make a plot of m versus t. And suppose that here we have Tc. So above Tc, the magnetization is equal to 0, and we know it because we have derived this before. So this is 0. Now, close to Tc, what happens is that you see that the derivative, so this behaves like a square root. So the derivative is infinite. So if I do the derivative of this quantity with respect to t, I compute it equals 0, I get infinite. No? So here I have something like this. So this is the behavior that we can infer from our expansion. So here the scaling of m is as the square root of the absolute value of t. Therefore, I have a singular behavior, not in the function, but in the derivative of this function that actually will show up later in the isothermal susceptibility that we will compute later. And what happens for a smaller, even smaller value of t, so we are computing here the behavior around Tc. For smaller value of t, of course, what will happen is that basically we will have a full magnetization. So with m equal plus minus 1 at exactly t equals 0, which is the full magnetization of my system, which all the spins are aligned in one direction, so which could be plus or minus. This happens at t equals 0. Okay. So you see that here I have a situation in which a disordered system, if you want, disordered. Whereas at t smaller than Tc, I start to have order. Indeed, for this reason, for order in the sense that spins tries to align the same direction. For this reason, the magnetization that we have introduced is also called model, kind of models, order parameter. When this order parameter, which is can be generalized to other systems, is equal to 0, we are above the critical temperature. When it has a finite value, instead we are below the critical temperature, and we see the developing of this spontaneous magnetization. We do not have external magnetic field. We have spontaneous magnetization, which is a spontaneous breaking of symmetry. Okay. So I hope that this is correct. I will check the result. Now, so to make a comparison with another system for which we have computed well, we have seen phase transition. Let us remember this plot here, which was found for the T for the liquid gas phase transition. That was something like this. Well, okay. So for instance, for water, we have something like this. So here there is a critical temperature. Is so here, if you concentrate on what happens around TC, we have that below a certain value of TC, we have a first order phase transition line. Then we have the critical temperature, and then we have a phase in which basically we cannot distinguish the liquid from the solid. This is a first order, the phase transition, which is a first order phase transition. Then at TC we have a second order, and then no phase transition. Okay, so the situation, although the system is completely different, the interactions are completely different. It's similar to what happens here in the sense that we have here a critical temperature TC, which separates a phase in which there is no magnetization from a phase in which a system could have finite magnetization in both directions. So you could have that your system actually is made of big clusters, for instance, in a sort of mixed phase, in which some of them are in the plus and some other are in the minus. So to some extent, it's similar to what happened here in the liquid gas when we have a mixed phase, okay? A mixed phase of liquid and gas. What is here will be sort of mixed phase between a system having a spin up and the other system having a spin down. Okay, something that is completely then and we have only magnetization at equal to 0. So actually, we find some behavior, and not only let's say qualitatively, but also quantitatively, in the sense that at some point we will compute what they are called the critical exponents, and we will see that those critical exponents have the same numbers in both the models we are using now for describing magnetization and also for the van der Waals situation. Okay. Now let me make some other plots. Forse faccio questo. What happens as I switch on the magnetic field? So what we have described before, it was for H equals to 0. Now, what happens when H is different from 0 is can be described qualitatively by these plots. Here I have still M, and here I have T. And actually now the situation will be something like that. Well, the situation for H equals 0 was something like this, in which here you have a divergence of the derivative of M with respect to T. This is the curve for H equal to 0. For H different from 0, and suppose that H is positive, we'll have something like this. So we have a smooth behavior. Okay? Smooth behavior of M versus T. And indeed, in that case, we do not have a real phase transition. It's more similar to a crossover, actually. So what happens between liquid and gas above the critical temperature. And okay, this for H larger than 0, where for negative H, So this is the plot, qualitative plot of M versus T for finite value of H. And then we will find an interpretation for this plot later when we'll compute the Helmholtz free energy, the behavior of the Helmholtz free energy will make clear what happens actually. And then let's make also plots, which is interesting, in which we put M versus H this time. Now, for H equal to 0 and for T equal to, well, for T smaller than Tc, well, okay, let's try first to make a plot of T larger than Tc. For T larger than Tc, there's nothing very strange, and this works now as a paramagnetic, if you want, because M is following the external magnetization, the external field. And what happens now if T is equal to Tc, which will have to something like this. Let me try to make a plot which is sensible. And we will compute actually this divergence. The fact that here I have a divergence will be shown in a moment in the susceptibility. So here at T equal to Tc, I have a divergence of the derivative of M with respect to H will explode. And we will compute it, maybe not today, but equal to T and H. We will compute it when introducing the isothermal susceptibility. Whereas for T smaller than Tc, we will have something like this. T smaller than Tc. Here, we will have something. Why? Because for T smaller than Tc and H equal to 0, we have two possible finite values of M here and here that correspond to this. Okay? So if you want here at H equal to 0 and T smaller than Tc, as I was saying before, we have a sort of mixed phase which reminds us, so we have a plateau in this plot, which reminds us is indeed the mixed phase that we have between liquid and gas or below the critical temperature. Okay? So you have a jump here, you have a jump of M around H equal to 0. Because if T is smaller than Tc and H has a negative value, I will get something like here. Whereas if it's a positive value, I will get here. Whereas if H is equal to 0, I'm sitting here. Okay? What reminds us this plot? It reminds us the plot of P versus volume below the critical temperature, in which we had, as I said before, a mixed phase here between liquid and gas. Okay? And we have a plateau here of the pressure versus the volume. Whereas here, if you turn around this plot, you have a plateau of M versus H. Okay? 47. Ok, forse ce la faccio fare un altro calcolino. So let's to study more in detail the behavior around the critical point, around the critical temperature. we have seen the scaling of the order parameter, which is m, as a function of small t. And now we will do, if you want, the first derivative and see that we start to find divergences, which are actually the signals of phase. So what we do now is introduce the isothermal magnetic susceptibility. Which is defined as follows. E, the function of t and h, and this is the partial derivative of m with respect to h at fixed temperature. Okay. Now, to compute this quantity, we have to start over with m equal to hyperbolic tangent of h beta times beta times h plus beta plus epsilon and q. Because I am deriving with respect to h, so then I need to keep the dependence on h. Okay. Okay, so let's try to do it. Derivative, partial derivative of m with respect to h at fixed temperature. Now this is equal to 1 divided by cos squared hyperbolic of beta times h plus epsilon and q. Then I have to derive the what is inside the hyperbolic tangent, and deriving with respect to h, I get a beta, which is there, beta. Then I have to derive this quantity with respect to h, so I will have plus epsilon q derivative of m with respect to h. Okay. Now, of course, you see that this is an implicit equation for m. So when doing the derivative with respect to h, I have to derive m with respect to h, but also this m must be derived with respect to h. Now, from this equation, I can now compute the derivative. Fortunately, it's easy, the derivative of m with respect to h, because now I can just need to isolate this term. And the chi of t at fixed temperature and magnetic field as a function of t and h, sorry, is equal to, well, I have to put this in here, and I have epsilon q minus this term, and then I have a beta. Okay, let me write down the result, and then let's check if it's reasonable. We have a beta, and then I have a cos h squared beta cos h beta, yeah, h plus n epsilon q, and let's close this. Just a moment. Minus epsilon q minus yeah, I forgot a beta here. I forgot a beta factor here. And then I have here epsilon q at beta. seno iperbolico di quell'affare, ma okay, let me check if this is correct, sorry. So I have this times this, and then I have beta epsilon q. Yeah, this should be correct, okay? So this is correct. So this is here. Okay, this is correct. Now this can be written when we at work at h equal to 0. I'm not sure I will finish this calculation today. Okay. So this is the general formula for the isothermal magnetic susceptibility. Now let's work at h equal to 0. So let's fix h to 0. Once we have computed the derivative, we want to compute what happens when the magnetic field is equal to 0. So the chi e of t0 is equal to beta. Here we have a cos hyperbolic of, here I have beta m epsilon q, and epsilon q divided by kb is tc, so I get m tc divided by t. As before. M tc divided by t, and similar for this. So minus tc divided by t. Okay, so what we do next is to find the behavior of the isothermal magnetic susceptibility above Tc and below Tc, and but close to Tc. So how does phi t of t0 behave around? Now for m, so for t larger than c, we know that the magnetization is identical equal to 0. Therefore, it is 1. So this cos is 1. And so the chi of t 0 is equal to beta divided by, here I have is 0, so that is 1. 1 minus tc minus t. It's equal to 1 divided by kb t. Here I have a t minus tc divided by t. T minus tc divided by t, kbt. It can be removed. And let me multiply by tc. So here I have a tc divided by t, and t minus tc divided by tc. And therefore, this should be tc divided by kb times t. Equal to tc divided by kb times t. So we have reduced, forse questa la lascio, that at least for t approaching tc from above, actually this is correct also not close to tc because we have not used an expansion, but in any case, for t larger than tc from above, approaching tc from above, we have the scaling of the chi T0, which behaves as 1 over T. Let me make an absolute value for reasons that will be clear later. In any case, for T larger than Tc, it's positive, and so you can put also the absolute value times K1 divided by K2. 1 divided by and then Tc. I think I made some mistake also here. Questo era beta, sorry. I think I made some mistake. Dunque, dov'è che sta?
Il PC va di
Ah, certo, ok, yes, thanks. So. There is 1 and there is 0. Now is it okay, right? Thanks. Okay, so here's the T of TC. Okay, so this is the behavior of the this isothermal compressibility magnetization around Tc for T larger than Tc. Okay, so you see that there is a singularity. Okay, when you have a singularity in the thermodynamical function as this one, this is a sign of phase transition. And indeed, this is basically the plot I was doing before, or when saying that when I plot M as a function of H at T equal to Tc, I have a divergence here of this derivative. Okay. This divergence of this derivative, which diverges as 1 over T, 1 over 0. Okay, so I think that for today it's enough because it's 1, and we will continue next time with the behavior of this isothermal susceptibility, and then I think we will finish next time with the Ising model. And for next week, I have to think what to do because there's no time to do Landau theory or universality. This year I was a little bit slower, and so I will see what to do next. Okay, bye bye.
Arrivederci.